Hey team, welcome to the Water's Well vodcast. Today we're going to be talking about acids, bases, and titration. We're going to be focusing on titrations, pH, acids, bases, and molarity, and then at the very end we're going to focus on calculations for both molarity and the pH. Let's go ahead and start and take a look at reviewing what titration actually is. So you'll remember that when we were doing this in class, you had to fill the burette up with some sort of titrant. In class we used NaOH for this. Down below, we had an acid in our Erlenmeyer flask. So this was kind of an unknown acid. In class, we knew what it was, but the idea is that you would have an unknown acid or base down at the bottom, and you're going to slowly titrate this into the Erlenmeyer flask in order to reach what we call the endpoint. So in this case, we had some type of acid to start with. We added NaOH into the mix, and since we put an indicator in it, eventually it changed into this pink color. So the pink color is telling us when we have some type of endpoint, right? When both things are totally equivalent inside the beaker itself. So here's what equivalence point looks like. This is a titration curve. So in a titration curve, we started off with some type of acid or base inside of a beaker. Now in this case, this mimics what we did in class. So we started off with an acid, and we slowly started to add a volume of base from our burette. And as we added the base, it started to increase the pH. This is something I'm going to talk about in a little bit. So the pH is increasing until eventually you hit this equivalence point. Once you hit this equivalence point, just one drop will make the solution turn pink. And so then it becomes more basic, and it increases until eventually you've got mostly base in your Erlenmeyer flask instead of your acid. Alright, so the equivalence point is super important. It's basically the threshold between being an acid or being a base. So here's an example. If we had an elephant that represents our base, and we've got people that represent our acid. It's a constant tug of war between the two inside this beaker. If one side's winning, the solution would be clear. If the other side is winning, then it would be pink. And the indicator is like this little fine flag on the rope itself. So whichever line it's on, or whichever side it's on, it's going to change its color. That's the equivalence point, when things are exactly equal and at a stalemate. Alright, so let's take a look and see what this looks like in terms of the chemistry involved. So here I've got acids and bases, hydrochloric acid and sodium hydroxide. So when you're actually combining these together, in previous lessons we've learned that these things dissociate in water. So HCl actually becomes Cl- and H+ in solution. Sodium hydroxide is going to become Na+ and OH- in solution. And when all four of these are floating around in the Erlenmeyer flask together, you get a double replacement reaction to occur, which is listed up here. HCl is our acid, NaOH is our base. You mix them together, you're going to get H2O. The H and the OH go together, so HOH, H2O. And then Na and Cl go together to form a salt. This is your double replacement reaction. So you may be saying, well, why is this a neutralization reaction? What's actually happening? Why are they balancing each other? And this is why. So in neutralization, H+ and OH- are opposites of each other, right? So this stands for a basic solution, the NaOH. This stands for an acid solution, HCl. When they come out together, they form H2O, which is completely neutral. So there's a constant struggle between these two particular ions, kind of like my doomsday Superman scenario over here. Constantly battling, but at a certain point they're completely equal to each other, and that means they are neutral. So here's what that looks like on the pH scale. Here's my titration curve again with the equivalence point. When they're both exactly equal, they're at a pH of 7, which relates to this up here. So here's a pH of 7 with just water by itself, water that we would drink, perfectly neutral. Anything below 7 ends up being an acid. So the lower the pH, the more acidic it is, all the way to the acid that we use in class. Anything above 7 is going to be basic, all the way up to the base solutions that we use in class. Anything in between is going to fall on the pH scale, so stuff that we eat, stuff that we clean with, different types of solutions like we test in class. So that's the pH scale overall. Equivalence point is where they're equal and where the pH is completely neutral. Alright, so I want you guys to go ahead and pause this video and try and answer these questions below. If you can't answer them, rewind, rewatch the beginning section before you move on. You can pause now. Alright guys, welcome back. we're going to go ahead and keep moving on. All right, so here is another version of the pH scale. I've put two pictures in here to represent the H plus ion. So pH stands for the power of hydrogen. Hydrogen is the key component in making something an acid or a base. In this example, I have the white flour representing the H plus ion. So here you can see there's one H plus ion and just a sea of red. That represents this right here. 1 out of 10 million would be H plus, which makes it basic, super basic, 14. So if there's no H plus available, it's going to be incredibly basic. On the flip side, if you've got all acid and barely any OH available, right, there's a lot of H pluses around, it ends up being extremely acidic, right, so a low pH, 10 million in fact. So you've got this discrepancy between these two kind of pictures or diagrams, being very little H plus, being a lot of H plus. Now I want to zoom in here for a second to show you something. I realize that this is kind of blurry, so bear with me. A pH of 7 is pure water, right? No ions whatsoever, because remember, they're completely neutral. All the H pluses have gone with the OH minuses. As you move down the scale, you're going to see that it increases by a factor of 10. So to go from just 7 to 6, it increases by a factor of 10. Going another step, it's going to go to 100, so on and so forth, all the way down to an extremely low pH. So going down 6 numbers on the pH scale is actually increasing this by a million H plus ions. It's also the difference between drinking pure water and stomach acid, which is nasty. And then it also goes the same direction the other way, except in reverse. So going from 7 to 8 means it's 1/10, 1/100th, so on and so forth. So the difference between drinking pure water and bleach, right? So above 7, remember, is basic. Below 7 is going to be acidic. All right, so here's some examples for your acids. I have the equation up top again. I gave a diagram here for lemons, just so you could get kind of a flair for what an acid would be. Here are the 4 main things that we're going to be dealing with for acids in here. Acids contain the H plus ion. They're pH less than 7. They typically taste sour, and some examples are HCl and H2SO4. For bases, I've got the same equation here again. NaOH is going to be representative for the base. Bases contain the OH minus ion. They're a pH higher than 7. Bases typically taste bitter, and examples are NaOH and BaOH2. All right, so based on what you've learned here, I want you to try and name the following as an acid or a base. Go ahead and pause now and try this out. If you can't do it, go back and rewatch what you just watched. All right, welcome back. So we've only got a few more things to go over, and that's calculations for molarity and for pH. The first thing we're going to go over is the molarity. So our equation is molarity equals moles of solute per liter of solution. The tricky part with these calculations are going to be that I'm going to give this to you in grams, so you'll have to solve for moles, and you're typically going to see this in milliliters first. You're going to have to convert to liters. So let's do an example problem together. In order to calculate these, you're going to have to be able to do these 3 things. Find formula mass, calculate for moles of a substance, and convert from milliliters to liters, like I just suggested. On the next page, we will go through an example problem together. So the problem says you dissolve 43.4 grams of HCl in 125 milliliters of water. What's the molarity of the solution you've made? So the first step is going to be to remember your calculation, which is up here, number of moles per liters of solution. Moles is equal to grams over the formula mass. So I'm going to have 43.4 grams divided by the formula mass, which is 36.5 grams. I got the formula mass from the periodic table. So the number of moles I have is 1.19 moles of HCl. All right, so once I have this, I have the number of moles that will go on top. Remember, we're solving for molarity. For liters, there is 1,000 milliliters in 1 liter. So if I have 125.0 milliliters, I'm going to divide by 1,000 in order to get 0.125 liters. and this is the second part that I need. Lastly, we can use our equation to solve. So it's simply going to be 1.19 divided by 0.125. And when you do that, you should get a final answer of 9.5 molarity. And that would be your final answer. You can go ahead and pause the video here, see if you guys can go through this example on your own and get to the same answer. And then after you're done, you can go ahead and move on to the example to try by yourself. So pause now if you want to try this one out. Alright team, so here is your example to try. Go ahead and pause here, try this out on your own, and I'll give you the answer when you're all finished. Alright, nice job. So if you did everything correctly, you should have gotten an answer of 26.07 molarity, or something very close to it after you're done rounding. If you're having trouble with this, go back and watch my molarity calculation. Alright, so what are you looking at when you're doing your titration with the molarity? The idea behind titration is that you've got some unknown value or some unknown molarity substance below and a known molarity up into your burette. So if you know what the molarity is here and you're dripping it into this thing and you reach an equivalence point, you can use some of the stoichiometry stuff that we've used, the molarity of the original solution, in order to calculate what this would be down here. This is what we did in the post lab, and we'll be working on some calculations in class about this as well. Alright, so pH, this is the last thing that we're going to learn. The calculations for pH require you guys to understand the symbols for concentration, which is this. So this means concentration of the H plus ion. That's what we're going to focus on. You're also going to need to understand scientific notation. So a number of 0.01 can also be written as 1.0 times 10 to the negative second. So these two are synonymous with each other. You also need to know how to use log on your calculator. So let's see what this looks like as an example problem. So I walk you guys through how I type it in on my calculator. You'll see kind of where the log button is. I know it's kind of blurry. That's the EE button that I'm hitting right now. And then I show you the screen up top. That's where the EE button is. It'll be different for each person's calculator. And that's what it should look like on your screen with an answer of 3.72. Alright, I'm going to do it one more time, but this time I am using the number for scientific notation when it's not in scientific notation. So 0.00019. But the rest of it will be the same. So you'll see how the numbers are different, but the answer remains the same. Either one of those ways is fine. You'll need to kind of figure out how you're going to do it on your calculator, but it's negative log of whatever the concentration would be. So negative log of the 1.9 times 10 to the negative fourth. Go ahead and pause the video, see if you guys can get 3.72 to show up on your calculators, and when you're done, we can move on to another practice problem. So go ahead and pause it now. Alright, welcome back. Hopefully you guys were able to figure that out, and now we will move on to the next one. So go ahead and try this one out on your own, pause the video, and I'll give you the answer. Alright, nice work. If you guys did this correctly, you should get an answer of 5.61 for your pH. If you're not, go ahead and go back and rewatch and see if you can figure out how to do the calculation. Alright, so that is it for this vodcast. Tomorrow we're going to be running through calculations for pH. Make sure that you are feeling good with the information that you got from this, and you'll be ready to roll for tomorrow. Alright, we'll see you soon. Bye.